Hello everyone and hello professor. My name is Feiyang and this is my final project for machine learning. Today I want to show you a system that performs two tasks at the same time: bird flock trajectory prediction and UAV intrusion detection in low altitude airspace. You can think of this first slide as the big picture of the project. On the left is the raw video input. In the middle is the unified framework that includes a trajectory predictor and a UAV detector. The predictor forecasts the flock's movement for the next 60 frames, and the detector checks whether a drone appears in the scene. On the right is the output: the predicted trajectory, the uncertainty, and alert when a UAV is detected. As small consumer drones become cheaper and easier to fly, collision risks are increasing, so combining prediction and detection is important for both safety and environmental monitoring. Here on the second slide is a simple explanation of how the model works. We start with the input trajectory and embed it with a linear layer and positional encoding. The center block is a two-layer lightweight transformer. Even though it's small, it can learn useful motion patterns such as turning or accelerating. The output is generated by a student T mixture density network head, which handles sudden or heavy tail movements much better than a Gaussian distribution. This makes the prediction stable even when the input has noise. So overall, the model is small, efficient, and flexible enough to capture flock behavior. Now in the third slide, I show two important experimental results. The left plot tests robustness to input noise. When we add noise, LSTM and the large transpeamer get worse quickly, but mini Forma keeps the lowest error, meaning it is more stable. The right plot shows long-term forecasting stability. As the prediction horizon increases, the large model's error grows fast, while mini Forma increases much slower and stays more reliable. These results show the model is not only small, but also very robust. On the fourth slide, we evaluate performance under different flock densities. Even as the number of birds increases, mini Forma keeps lower errors in the baselines. The right pie shows the system latency breakdown. Our prediction module takes only about 5% of total latency, and the system runs at 616 frames per second, far beyond real-time requirements. So the model is accurate and extremely fast. The fifth slide shows how we prepare data for evaluating UAV detection. Real UAV intrusions are rare, so we build a small synthetic pipeline. We use real UAV assets, bird-only backgrounds, and combine them to create augmented frames. This lets us test the detector under different lighting, scenes, and flock configurations. The sixth slide shows UAV detection results using OWLVIT. The detector works in a zero-shot way. We simply give prompts like drone or UAV, and the model can detect objects without extra training. Across different backgrounds and angles, it maintains high recall and almost no false alarms. These examples show that the detector is reliable and complements the trajectory predictor well. This final slide summarizes the quantitative results. Mini Forma achieves the best ADE, FDE, and NLL values, especially for long-range prediction and uncertainty calibration. This confirms that a lightweight transformer, combined with a student TMDN, is both effective and robust. Okay, that is the introduction of my project. Since my group only includes myself, I faced a few practical challenges along the way. First, the raw trajectory data was quite noisy. To handle this, I consulted some mentors, then used tools like Pandas to build a pre-processing utility that automatically generates a large number of tables. These tables were then imported back into Pandas for calculation, meaning the data didn't need manual intervention. It was a high-quality automated approach. Second, I found it really challenging to source any existing datasets that included both birds and UAVs. To solve this, I created my own dataset. I took about 20 bird-only video clips and composited UAV assets into them, and then tested these 20 modified videos among a set of 100 to see how well the detector could identify UAVs. The accuracy was over 90%, which was a strong indication of success and practical value. In the future, I could integrate actual video footage to refine this even further, or even record my own material. Thank you for listening.